going to have an instruction here that occupies 32 bits. We've got an opcode, a source register, a destination register, and an immediate operand. Is this, there are 60 opcodes, 32 registers, and the question is what values can be stored in the immediate operand. The trick, of course, is to know how many bits you're going to have to use for each one of those fields. If I have to represent 60 different opcodes, how many bits do I need?
6.
8.
6.
Well, I heard 6.
6.
That's the correct answer, but why is it the correct answer?
2 to the 6 is more than 60.
64.
Yeah.
Barely, yeah.
2 to the 6th is 64, which is the smallest power of 2 greater than 60. That's really what you're looking for. Okay, so we've got 6 bits here. How many bits do I need for each register?
5.
5. 2 to the 5th is 32. Okay, so how many bits have I got for my immediate operand?
60.
16. Now, the problem specifies that it's a 2's complement number. Yeah, assume IMM is a 2's complement value. So the question is, what's the range of values that I can represent in 16 bits?
From negative 2 to the 15th.
The largest positive number is this. Now, if you want to figure that out quickly, just note that it's 8 minus 1. Now, it's not 7,999, of course, because those are base 16 numbers. There's another way you can look at it. If you look at this number, it's
Where did the 8,000 come from? Space 16.
adding 1 to this number.
Okay.
It's not really 8,000, it's
No.
8,000 to the 60.
Yeah.
Right.
That's one of the problems with working in different number bases. You have to look out for that. Okay, so if we write it in binary, it's 2 to the 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So I can write that as 2 to the 15th minus 1. I can also write it in this one as 8 times 16 to the 3rd power.
Minus 1.
Minus 1. If I do this conversion, 8 is 2 to the 3rd, 16 is 2 to the 4th, to the 3rd, 2 to the 3rd times 2 to the 12th minus 1, 2 to the 15th minus 1. Well, if we can't maneuver those things around like that a little bit, we're in trouble.
This might be a stupid question. How'd you get the 8 times the 16 to the 3rd?
Because in any
You
number-based
change it to the
system,
10th
this is times the base to the 0 power,
base.
1st power, 2nd power, 3rd power. Okay, it's the same way that I ended up with 2 to the 15th by counting places across here on powers of 2. If this were in base 10, why do we say 8,000? Well, it's 8 times 10 to the third, 10, 0, 1, 2, 3.
Cool.
Okay, that's the basis of the positional number system. Okay. Well, I've figured out, this is one of the really common numbers that you come up with, because 16 bits is a relatively common numeric size. The largest negative number, well, is in absolute value 1 more than the positive limit. And so you end up with minus 32,768. Okay, these are all considerations that come into play in the design of a computer system. It kind of demonstrates in the long run, if you're working with something of a fixed length, you might say, well, gee, I'd like to have 500 registers. Well, you have to recognize that you pay real estate for that. If you have a lot of registers, it takes space out of your instruction to specify what you're coming up with. So that's kind of the lesson of that. 4.8 is a similar problem, but I guess we won't really take the time to go over that. Okay. Hexadecimal, octal, you got to be able to manipulate those things, because everything we do from here on is going to be in these number bases. So you need to be very familiar with how they work as we set things up. Now, the system that's used here is called LC3. LC stands for Learning Computer, version 3. It's a relatively simple system. We'll go through it here as we work into it. It's designed as a tool for learning how these things work.
What'd you say the LC stands for?
Learning computer.
Okay.
I thought it was level.
It isn't a real system. If you have not downloaded the software for working with it, do it, because you're going to be writing code for this thing and executing it. That's basically what the rest of the course is about. Writing here. They have developed a really good environment for working with it. The editing system is good, and when you go to execute your programs, you get a nice display up there that shows you what's happening. You can go through the programs one instruction at a time and watch how things change. It's very useful in terms of finding errors. It's a good system. People say, well, why don't we learn the Intel assembler that's used in all the PCs that everybody's got? Frankly, the reason is it's an abominable system. It is just incredibly bad. Virtually every architecture book I've ever come across uses that as an example of a poorly designed assembly language. It is really hard to work with. Well, how did it get to be where it is? Well, the problem with it is that in the early days of small personal computers, there were several different processors out there. Our friends at Big Blue, IBM, decided that they would use this Intel chip. And because of their reputation and their market dominance, it was accepted and got to be widely used. As we were able to do more and more in less and less space, and therefore expand these processors, that original 8086 was an 8-bit processor. It would add 8-bit numbers. How big a number can you work with in 8 bits?
256.
255. That's it. So in order to add numbers bigger than 255, they had to do it in stages through the processor. Add a piece of the number and then add another piece of the number and work about carries in between and all the rest of that. So eventually, why they widened that and got out to a 16-bit processor at about the 286 level. But in order to keep their market share, they said that this 16-bit processor has to be able to use all of the old 8-bit programs. And so they did a thing called backward compatibility. And then when they went from 16 to 32, they did it again. And it generates some real problems in the way you work with it. I'll comment on some of the differences as we go through. Suffice it to say, a semester would not be adequate to learn the program on the Intel chip. It just isn't. It's much more complex than that. The LC3, as it is set up, let's just see here. Yeah. The basic organization is that it has 8 so-called general purpose registers. Let me explain what we mean by general purpose. The LC3 is a 16-bit system. That means that addresses are 16 bits. Now, since addresses are not signed numbers, we get back to this thing we worked with here before. You don't have negative numbers for addresses. There's no mailbox numbered -44. Okay? That means that we have 65,500 30 that doesn't sound right to me.
536.
Yeah, that sounds better.
Yeah.
There are that many locations in memory. Each stores a 16-bit number. Most of the modern systems that we work with are what we call byte addressable. That is, each 8 bits or byte in memory has a separate address. So you get these, the new Intel 64-bit processor, your addresses are 64 bits long, and each one of them references a memory location that only holds 8 bits. Now there are some reasons for that, and you'll see that as we go through here and work with this, we pay a bit of a price for not doing that here. This 16-bit number is called a word. And so this system is word addressable, not byte addressable. You cannot reference individual bytes directly. These 8 general purpose registers are also 16 bits. And what we mean by general purpose is that they can be used for data or addresses. Intel's biggest competitor back in the early days of things was Motorola 68,000. It had 16 registers. 8 of them could be used for data, and the other 8 could only be used for addresses, and vice versa. If you wanted to use a register to get into a particular location in memory, you could not use a data register to do it. That's what we mean when we say general purpose. These 8 registers can be used however you want to use them. That's what it comes down to. There are a couple of limitations, but in general, that's what we work with. Well, let's see. Oh, okay. Let's look at this. They do an example here. The registers are numbered as we do everything at this level, starting at 0 rather than 1. Down here on the bottom of page 116, if you have your books, he has some values in these registers. I'm not going to write out all the bits. Well, I will for the first one. 3, 4, 11, 12, 13, 14, 15, 16. When we write out binary numbers, it's usually a good idea to write them either in groups of 4 or groups of 3. Because then it's easy to convert from there into hexadecimal or octal. And whether you choose hexadecimal or octal, there are some considerations. We'll talk about those. Let's see, register 1 is basically the same thing except it's got a 3. Register 2 has a 5, and register 3 has a 7. Now, the others are all negative numbers. So register 4 has all 1s except for a 0 on the end. Register 5 has 1 with 2 zeros on the end. And, okay, I challenge you to tell me what was in register 6. Could you do it?
Is it 6? Negative 6?
It's FFFA, right?
Yeah, what's actually in there, of course, is
6, negative 6.
1010 is
Oh,
A.
with the value?
Let me show you a slick way to convert that. It's a negative number, first of all, because of the 1 here. All these things are stored as 2's complement. So to convert that into a positive number, go through and subtract each of these numbers from 15. Except for the last one. Subtract the last one from 16. Or subtract it from 15 and then add 1. Doesn't matter if you subtract it from 16 from minus 6. Slick?
Right.
It's really a relatively easy process once you get used to it.
So you're minusing out F, 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 and then you're minusing out.
Yeah, subtract each of these from 15. Well, that is a 15.
That is a
So
15,
minus
so
15, 0, 0, 0. Subtract 10 from 16 gives you 6. Okay,
So that's a negative 6 then?
Yeah.
That-
that's minus 6.
Why don't they just do, for the registers, because it goes 1, 3, 5, 7, and then negative 2, 4, 6, 8. Why don't they just do 1 through 8, or 0 through 7? For the, memory, I guess.
I'm not sure what you're saying.
I remember reading about this in the book, and it talks about the values, in your register there, 1, 3, 5, 7,
Uh-huh.
register 0 through, 3, and then negative 2, 4, 6, 8. Why didn't they just do 0 through 7?
Because they wanted some data. These particular numbers don't have any significance except that they represent data that we're going to use to demonstrate how instructions work. That's all. And they wanted some positive numbers and some negative numbers, so
Okay.
just make some up. Okay. What we want to look at now is an example of an LC3 instruction. Well, okay, we'll go all the way down to the bits here. The bits are numbered 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13, 14, and 15. We're going to look in particular at an add instruction. And this is the way the bits are actually used. This is a source register. For our purposes here, these 3 bits are unused. You'll see what they're for later on. This is another source. This is our destination register. And these last represent the opcode. And the particular instruction now that we're going to work with here looks like this. Now, here's the way this thing actually works out. That opcode says add. This thing says put the result of the add in register 2. You see, when you do an operation like this, there are really 2 things that you have to work with. First one is, what is the operation you're going to do? In this case, it's add. Now then, you have to specify then, what is it you're going to add? Those are the source operands. This is register 0, this is register 1. Okay, this thing says add register 0 and register 1 and put the result in register 2. This is the operation that that instruction would perform. So what would we do here? Well, 1 plus 3 is 4. So we would come down and this would be replaced by a 4. And the two source operands are not modified. Okay, that's an example of how the thing works out. Now, let me show you something about that instruction as it's stored in memory. I can take the value that's in there if I write that in octal, I get 0, 1, this is a 2, 0, 0, 1. Now if I write that thing in octal like this, yeah, I can say, well, here's my opcode. This is my destination register. This is source 1, and this is source 2. At the present time, this is unused. There are times, we'll show you some things later when we talk about the instruction set in a little more detail what's going on. Okay, in other words, now writing that thing in octal, I can pick out very readily the parts of the instruction. I mean, the register numbers are just right there. I don't have to do anything with it. Now, on the other hand, if I were to go through and do this thing and convert it into hexadecimal, I would come up in hex with 1004, 0, 1. Not very helpful. The opcode part is cool. 1. Yeah, that's an add instruction. But the registers, I can't decipher them because each register is specified by 3 bits and things have been grouped together in groups of 4 bits.
Why is that 4 not a 2?
Because looking at 4 bits, it's 0, 1, 0, 0.
That's 4.
See, that's the problem. I'm writing it in hex, and so the things have been grouped into groups of 4 bits, and only 3 of those 4 bits are actually used to specify the register.
Yeah, part of it's diving into the source of the other one.
Yeah,
I mean,
exactly. You get that overlapping in there. I make that point because whether you translate these binary things in memory into octal or hexadecimal depends on the nature of the machine that you're working with. When you're working with groups of 3 bits to specify a register, 3 bits, octal. If you've got 16 registers, you'd be working with 4 bits, it's probably best to do it in hex. Surprises a lot of people that a lot of the supercomputers, everybody says, oh, 16 is more powerful. You know, this one works in hex. That one works in octal. Oh, hex is better. It's more powerful. No, it's not. Doesn't have anything to do with it. The machine itself is working in binary. It's just how it communicates with you. Some of the big supercomputers have, instead of 8 registers, they have 64. They work in octal. because 2 octal digits will specify 0 through 63, the 64 registers. You write them out in such a way that it's easy for us poor humans to grasp what's in there and decipher it. That's what makes the difference. You do it in the easiest way to decipher. So just watch that kind of thing. If we have 4 bits for an opcode, oh, let's see, there was a hand back here, and I kind of ignored you.
Oh,
You
that's
did-
fine.
Go ahead.
I'm just thinking, don't worry about it.
Okay. If we have 4 bits then for an opcode, how many different instructions can we have? 16. They can have opcodes 0 through F. And it's kind of a restricted instruction set. It's not very
Yes.
extensive. And that's one of the reasons why we do it. There's not a lot to learn. The actual instruction set is here. It's also on the inside back cover. Yeah.
That is the ISA then? That is the ISA. Or is
Well,
it more than
yeah, that's the thing that defines the instruction set architecture. You know, what are the instructions that you have available?
Is that the assembly language?
Mm-hmm. You'll notice here, for example, that there are 2 different add instructions, and they differ in this bit right here. If that bit is a 1, then the remaining bits are not used as registers, they're used as a so-called immediate operand. We'll get into working with that. But there are limits, then of course you've only got 5 bits left to work with. We're not going to talk too much about this instruction set. Just look at it briefly. There are 2 adds, there are 2 ands that perform a logical and. Just exactly in the way that you would think about that. BR is a branch instruction. Then we've got some jump instructions. Jump and then jump to a subroutine. And then another subroutine jump that, where the address is done differently. Some load instructions that allow you to move data from one place to another. We have a logical not, return from subroutines, and we've got some store instructions and a trap instruction, which we'll just have to talk about later on. And you see that there's 1 opcode that hasn't been used. What's missing?
Subtraction.
What?
Subtraction.
Subtraction,
Multiplication?
multiplication, division. Not unusual, by the way. Only in fairly recent times have processors been built that have built-in multiplication and division instructions. It's always been done in software. You have to write the code to do it. So that's something to look at. And we'll talk about that. And we'll either write or maybe have you write a multiplication routine before we're through with the course. Data types. One of the things you have to recognize, this refers back to the von Neumann architecture, the contents of a location are interpreted see, I have this nice octal number that's stored here. How do I distinguish between that and the corresponding numeric value? How do I know whether what's stored in that location is an instruction or a data value? It's all done by context in the von Neumann approach to things. Some of the original thoughts about computers, they had separate places for instructions in this part of memory or this block of memory, and data was stored over in this one, and never the two shall meet. Von Neumann says, no, we can just use one block of memory and everything is interpreted based on context, what's happening when you hit that instruction. This could be an instruction. It could be a 16-bit integer. Could be a floating point number. Could be just about anything. Some of the assembly language books I've worked with have an exercise where they give you this kind of thing and say, if that's an instruction, what is it? If it's an integer, what is it? If it's a floating point number, what is it? And you just look at the bit pattern, and it just all depends on how you choose to interpret the thing. The basic data type on the LC3 is really just a 2's complement integer. That's really what we have in there. Now, when we say that, it isn't strictly true, because by handling the thing in software, we can manage to interpret it in different ways. Now, through most of what we do here, we're going to be working with integers and occasionally with characters. Now, characters only occupy 8 bits, which is why most contemporary machines are byte addressable, so that they get in and work with character by character. We have a problem doing that here, but not going to do a whole lot of character manipulation. We'll do some, but not a bunch. Basically, this is what we'll work with a few exceptions here and there, but basically that's what we talked about. Now, there are a couple of other things that we need to look at here, and then we'll actually get down in and look at the instructions and see what's going on. We have to talk a little bit about how we get a hold of things in memory. How do we reference? We know a little bit here about how to reference the registers, but we've got all this other 65,000 words of memory out there. How do we get a hold of them? How do we get numbers out of there that we can work with? How do we store numbers into there? This is what we call addressing modes, and we'll show you how we work with those, and then we'll start actually looking at some code and show you how we can write programs to do these things. Okay, any questions? Yes, sir.
Can we get, like, since we've been kind of ping pong or tennis between 3 teachers, can we get some things that you'd really like us to know so that we're prepared for the future lessons?
That's fair enough. Yeah. I'll just make a comment here initially. You really need to know how to convert back and forth to decimal, hexadecimal, octal. You need to know that process. You need to know the 2's complement. Those are some things that just come up right off the top of my head. Because this chapter, you're going to be writing code, not with add, but you write code this way. So you've got to be prepared to work at that level. Gotta be able to work in binary and write the things out. Okay, any other questions? Yes, sir.
Homework.
So the schedule that Ryan had on Blackboard, are we still using that, or?
I can't answer that at this point because I haven't seen it.
You want to turn an assignment that was due today?
Yeah, if there's an assignment due, yeah, you better turn it in.